Good Sunday morning to you. So this is it. This is the last lecture we're going to do. Got a couple little topics to talk about. The first is Snell's law. I already introduced Snell's law to you. Must be sweating. I got some sweat marks on my paper here. But Snell's law is the law of refraction. And Snell's law basically says that the index refraction in substance number 1 times the sine of the angle in substance number 1 equals the index refraction of substance number 2 times the sine of the angle in substance number 2. And we can use that to figure out how something is going to go into or out of a new material. So let's practice. Let's pretend we have a horizontal surface where below is water and above is air. Now, this is very normal because if you have a body of water, the air is above it. Let's bring in some sort of laser light or something, and let's bring it in at a 45-degree angle. That's measured away from the normal here. So this right here is going to be 45 degrees. And what I'd like to know is, where does that laser go when it enters the water? Does it continue straight? Does it bend away from the normal, like a shallow angle in the water, or does it bend towards the normal and go to the bottom of the body of water more quickly? And we know that when you go from a thin to a thick substance, that you bend towards the normal. So we're going to be bending into this kind of angle. But I'd like to know, what is that angle right there? Well, luckily, we do know something. The index refraction of air is 1.00. I know it's 1.0003, but to 3 sig figs, this is fine. Water is 1.33. So if we take air to be the number 1 substance and water to be the number 2 substance, we can go ahead and use Snell's law. So index refraction number 1, which is 1.00, times the sine of the angle in substance 1, which is the sine of 45 degrees, is going to equal index refraction number 2, which is 1.33, times the sine of the unknown angle, which is the angle in the water. Okay, 1 times something is just something, and we have to divide by 1.33, so this side is going to be sine of 45 divided by 1.33, and that's going to equal the sine of the angle in the water. And in order to get just the angle, we have to do inverse sine to both sides. So we need inverse sine of sine of 45 divided by 1.33, and that's going to give us theta 2. Now, you have to do the thing that's in the parentheses. You have to do it first before you do inverse sine to it, because that's the way inverse sine works. It's an argument on an entire function. So let's go ahead and do that. Let's see. There we go. I think you can kind of see this way. So let's take sine of 45 degrees, enter, 0.707, that's correct. And then we're going to divide that by 1.33, enter, that's 0.531. And now we're going to take the inverse sine of that shebang-a-bang, and that's going to give us 32.1. So the angle inside of the water is 32.1 degrees. And yes, 32.1 degrees is less than 45, so we have bent towards the normal. So if you want to shine a laser pointer in on your goldfish, it will bend towards the normal. If that will help you aim, so be it. Let's do another one. Let's say that we have some laser and it's inside of glass, and it's coming out into the air. Okay, so it's coming out of a glass window or something like that. And let's do it again at a 45-degree angle to the normal. And now we know that because we're going into air, we're going to bend away from the normal. We're going to bend this way. And there we go. Let's find out what that one is. So glass has an index refraction of 1.5 or so. Air is 1.0. So we're going to say 1.5 times the sine of 45 degrees equals 1.0 times the sine of theta 2. Dividing by 1 is not necessary, so what we need is the inverse sine of 1.5 times the sine of 45 degrees. And that's going to be equal to theta 2, and that better be a number bigger than 45. So we get out the old calculator, and we do inverse sine of 1.5 times sine of 45, end parentheses, end parentheses. Okay, let's just do this the old-fashioned way. 1.5 times sine of 45. 1.06, that's fine. And then we take the, That is not cool. Something has happened here. Okay, all right, hold on. Notice that the argument here is greater than 1, and that ain't legal. You can't take the inverse sine of something greater than 1. Sine doesn't go that far. Let's make this angle a little smaller. Let's go ahead and change this to a 35-degree angle. And now let's see what happens. So this becomes 35 degrees. And we're going to go ahead and 1.5 times the sine of 35. That's 38, so let's make that 35. And that's a number less than 1. And then we're going to take the inverse sine of that and get 59.53. Okay, it did grow, 59.53, 59.5 degrees. It did grow from 35 to 55. Maybe that's what's going on here. Maybe as we get closer and closer to 45, this one is growing so large it actually gets to be 90 degrees. And in fact, that is what's going on. I accidentally discovered something called total internal reflection. Total internal reflection, otherwise abbreviated TIR, is refraction gone bad. That is to say that we're going from, okay, I need a little more of this. There we go. That is to say that we are going from a thick material to a thin material, and we're doing so at such an angle that it can never really escape. So this light is trying to leave at some angle, and I'm going to call it the critical angle, and then the light bends and goes right along the surface. So the angle out here is 90 degrees. And the question is, did that light really get out of the material or not? Is it possible to be at some angle so that this is 90 degrees? Yes, it is, and we can solve for what that is. So we take the index of refraction of the thick material and multiply by the sine of this critical angle, and that's going to be the index of refraction of the thin material, which is normally 1 because it's either air or vacuum, and the sine of 90 degrees, which is also 1. So what we have here is that the critical angle is going to be the inverse sine of 1 over the index refraction of the thick material. And if you try to go out of a thick material into air or a vacuum, and you're at an angle greater than the critical angle, then what will happen, here we are at an angle greater than the critical angle, it will just bounce off the surface and stay inside. It will be reflected. That's why this is called total internal reflection. What is the critical angle for glass? Critical angle is going to be the inverse sine of 1 over 1.5. The inverse sine of 1 divided by 1.5 equals 41.8, or about 42 degrees. So if you try to leave glass at an angle greater than 42 degrees, it won't happen. For water, the critical angle is about 48 degrees. And so what that means is if there is light inside of a glass of water, it won't be able to get out if it tries to leave at an angle greater than 48. And I experienced this once. I was sitting inside of a pool. Here's me snorkeling. And I looked, and when I looked straight up, I would see the birds and the sun. That's a theta, not a sun. Got carried away. And things like that. When I looked over here, I would start to see like the side of the pool and the house. That was really weird. The side of the pool and the house is not sideways. It was at about 45-degree angle. And by the time I looked over here, so that light was, along this angle that was greater than 48, the surface of the water became silvery and reflective. And I remember because a friend of mine has an inlay in his pool, a little tile mermaid, and it's on the bottom of the pool in the shallow end. I could see it reflected off the surface of the water. It was kind of cool. So when you look in the pool, you've got about a 48-degree window in which you can see all the stuff outside the pool, and then the surface of the pool becomes reflective. If you really want to see this in a hurry, get yourself a glass of water in a clear glass, fill it up part way, and then look at it from the bottom. There's your eye looking up through the bottom at this thing. And for various places you can hold the glass over your head, the surface of the water becomes a reflector and shows you the floor. Total internal reflection is refraction gone wrong, and it causes perfect reflection at the surface. It's the secret to fiber optics. When we put light into a fiber optic cable, it can't get out. Therefore, all of the light, almost all of the light, makes it to the other end of the cable. So these cables can be very long and still carry our data, and they can carry it at very high speeds because we're using visible light as opposed to radio waves. So total internal reflection is Snell's law gone wrong. Another time when Snell's law goes wrong is in the phenomenon of dispersion. And dispersion is where colors are separated. By refraction. And so there's a really famous photo, and it's a triangle of glass called a prism. And what happens is we have some white light going into the prism at this angle. This is white light. So it contains all the colors. And the truth of the matter is that the index of refraction for red is maybe 1.5 in glass, but the index of refraction for green is 1.51, and the index of refraction for blue is maybe 1.52, which means that as the colors get into the glass, they separate. The red doesn't bend away from the normal quite as much as the green does, which doesn't separate or bend towards the normal quite as much as the blue does. And when they go to leave the prism, it goes the opposite way. The red bends away from the normal, but not quite as much as the green does, and definitely not as much as the blue does. And we wind up separating white light into its colors. And if you think that this picture looks familiar because it is on the world's most popular album, Pink Floyd's Dark Side of the Moon, which is a great album, but I think that they sold so many copies because they kept putting it out with different masterings and re-recordings and gold this and extra tracks that. So people bought this thing multiple times. Who knows? It's still worth a listen. Isaac Newton was one to show that this dispersion was not just a function of the glass, and that colors, once separated, could never be recombined. He took a second prism and held it in an opposite orientation, and due to the refraction and dispersion happening in the opposite way, the white light was recombined. So he showed and proved that white light is made up of the colors, and the colors can be recombined into white light. You know, he was a borderline genius in some aspects of his life. There's another way to get rainbows, and sometimes that has to do with interference. That is to say, if you've ever dropped gasoline on the ground at a gas station, you know, so you weren't being very careful when you filled up mom's car, you may have noticed the edges of the gasoline drop had a rainbow pattern to them. And that isn't from going through the gasoline. It's actually from bouncing off the back side of the gasoline and coming back. There's an interference pattern. There might be some dispersion, but it's more of an interference thing. I want to talk about polarization briefly, and then I would like to show you why refraction makes bodies of water appear to be shallower than they really are. So let's talk about polarization. And this polarization is not the political polarization where people separate themselves into two camps, one thinking one way, one thinking another way, which, by the way, doesn't necessarily have to be a nasty thing. Certainly, I get the feeling our country was founded on people arguing different positions. The thing that gets nasty is when they go right to name calling and you're a duty head. It's just hard to watch. Polarization in this case refers to the orientation of the electric field. Remember that light is made up of an electric field vibrating in one plane. Here I'm going to draw it up and down, and a magnetic field vibrating in another plane perpendicular to it. And that's an upright polarization of light. I could put a little sign right here that goes up and down. That's up and down polarization of light. But, you know, when you turn on a light bulb or an LED or anything like that, there's all kinds of different polarizations come out. You could even get a polarization where the electric field is horizontal back and forth, and that the magnetic field is the one that is up and down. And that's perfectly legitimate. That might be a horizontal polarization. And light that you get from light sources contains all kinds of different polarizations from all kinds of things that just made a piece of light. However, a couple things can happen. First of all, if light that is polarized in a vertical way hits a horizontal surface, so here's a piece of light, it's going to skim off the road, or let's make this a road that's covered with water or something. If it has a vertical polarization of the electric field, the water or whatever is reflective on here has a tendency to eat up that electric field and kill the light. But light that has a horizontal polarization is able to bounce off. So the reflections off of horizontal surfaces tend to be horizontally polarized. In other words, not all the light reflects off. Some of it is absorbed. And preferentially, light that is horizontally polarized with the electric field side to side is able to bounce off. And so this means that if you could wear a set of glasses that only allowed vertical polarization of light in, then these reflections would be reduced. And that is indeed what happens with a polarizing lens. Polarizing lenses can take the horizontally polarized light and not let it pass through only vertical polarized light. So if you were to look at the sun, you would see you'd see this ray of light, but not that one. And when you look at the reflection, this one didn't reflect, that one did, but you can't see that one. So it cuts down on reflection. I swear by polarized sunglasses. I spent an extra, whatever it is, $30 to get polarized sunglasses. If you look at water, you are not as stunned by the shimmery surface of the water. When you look into someone's car, there's less glare. You can see into the car. This is why motorcycle police officers prefer to wear polarized sunglasses so they can see what you're doing in your car. It was conceived at one point that we would put polarizing tint on our windshield so that you would not be blinded by oncoming headlights. The downside is you wouldn't see oncoming headlights quite as well. One of the most interesting things about polarizing lenses is that if you were to take a polarizer, a piece of polarizing plastic that allowed vertical polarization to go through, and you were to superimpose on top of it a piece of polarizing plastic that allowed only horizontally polarized to come through, you would find that 50% of the light would get through this one by itself, 50% of the light would get through this one by itself, but when you overlap them, 0% would get through in this section right here. It goes dark. And this is actually how LEDs work. I'm sorry, LCD, liquid crystal display. So if you're ever looking at any LCD displays, like a gas pump usually has an LCD display that tells you that you put 15.612 gallons in your tank. If you're wearing polarized sunglasses and you tilt your head, you can make this display disappear, because you'll get a situation where you're polarizing sunglasses and the polarization of the device, your calculator uses the same kind of thing, they cancel each other out. So there's some fun polarizing effects that can happen with that. The hologram that creates the Michael Jackson or the Tupac Shakur or something like that, I had a brush with a genius when I was in grad school, and he apparently has the patent or one of the patents on how that is done. And his patent starts off with the word polarizing blah 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 with a blah 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 laser field. And so I tried to read this thing, and sleep was induced very quickly. Yeah, so you can look it up. His name is Doug Burke, or Douglas Burke, and damn genius. Okay, so last thing I want to show you. If you stare down into a body of water, and let's say that this body of water is, say, 17 feet deep, because this happened to me. I used to like to jump off of high places when I was a kid into water. Normally you can't see the bottom of the water, and one time my grandmother took me down to Belmont Shore. There used to be a really big pool, Olympic pool there, and for some reason the diving platforms were not locked. So I climbed up to the 5-meter platform and I stood out over the edge. Now, 5 meters is about 15 feet. That's the kind of distance I would throw myself into the river or a lake. However, this was clear water. And although it said on the side of the pool 17 feet, I looked down into this water and it looked maybe 12 feet deep. And I want to show you why. So let's imagine there's an object. Let's make it be a diamond. Because, you know, diamonds. And I'm just going to be standing up here. But I'm going to be trying to figure out with the depth of field, how far down is that? So we can track some light from the diamond. First of all, any light from the diamond that goes straight up along the normal will continue straight out. And so that ray will go straight out of the pool. But any light that goes at an angle is going to bend away from the normal. Oh, good God, Harmon, there we go. A little bit further away from the normal than it was. And so your brain is going to see these two diverging rays, and your brain is going to trace them back to where they appear to have come from, and you'll find that this distance here is about 2/3 of the distance, maybe 2/3 to 1/4, or 3/4, I mean, of the distance of the total depth of the pool. So if it's 2/3 of 18, that would be about 12. So it was a little less. It looked a little less than 12 feet deep. Standing over 15 feet above water that's only 12 feet deep makes you think you're going to hit the bottom when you jump into it. So I actually freaked out. One of a couple times in my life that I've done this, I freaked out and climbed right the hell back down. I just didn't think it was possible. Now I should have known it's possible. People do it all the time, but I was like a throw yourself off the cliff guy, not a skilled diver, so maybe I thought the divers did some sort of arcing or something, and I don't know. But this is why bodies of water look shallower than they really are. It's because of refraction and the fact that diverging rays of light are how you perceive depth. Okay, so my plan, it's a Sunday morning here, and it's already hot. My plan is to watch my own videos. Yeah, going to schedule a nap this afternoon, and watch my own videos, and jot down some notes about what were the important things, and I'll do a quick presentation for you Monday, Tuesday on what I thought were the important things, and then late next week I'm going to open up the Kahoot quiz. All right, talk at you later.